Um, I've been seeing a lot of discussion on Piazza about homework 1, so I'll just remind you about it. Homework 1 is due today. If you haven't started yet, please start after the class, not right now. Take advantage of office hours. I think, well, there isn't one today anymore, but I hope you've taken advantage of office hours. And there's a lot of discussion on Piazza, so keep that going. There was a bug in our auto grader that we fixed, and we made an announcement about it. So it should have shown up on your Canvas announcement. The short version is basically we ended up giving you really high points if your code was really, really, really bad. So we fixed that. So if you feel like you submitted an empty file and got a perfect score, well, not anymore. Yes.
So we need to recheck the current grade.
Do you need to recheck the current grade? I think just to be safe. Yeah. The bug should only affect those cases. I think Oliver, you can correct me. If your files were empty.
Like a folder with all the code in it. Like it needs just the 3 files.
Yeah, rather than the 3 files, if you uploaded a folder. If you didn't do either of these two things, then you should be okay.
You can upload it as a zip, but you can just upload the 3 files and it'll work fine.
Yeah, you can just upload the 3 files. And if you feel uncomfortable about it, check. I think it's quicker to check, right? Yes.
On Canvas, the grade for the maximum total points is showing 0 for homework 1.
Yeah, we'll fix that when we are grading it. It's 100. It's some number. It doesn't really matter because we'll scale everything up and down later on, but it's not 0 for sure. There is there's a question on Zoom for the undergrad students. There are a few grade scope tests on collision. Do we need to worry about that? No. For undergrad students, the only tests that matter are the ones that are for the questions that you are responsible for. So don't worry about the collision entropy, which is only for grad students. You can try to implement it for fun if you want. You won't get points for it, but you get bragging rights. Yes.
Does the code automatically regrade?
Does the code automatically regrade it? I think not. So just to make the thing a little bit more complicated, this is our first time experimenting with grade scope for this class. So part of the problems are also because we are figuring out grade scopes auto grader. I think it should not. I think if you upload it, it triggers a grade.
Right now it says I've got 0 points out of 75, even though before it said 75 and 75.
Try uploading it again. Yes.
In the worst case scenario, we'll like manually grade every submission.
Yeah, that's the other thing. If it turns out that there are some inconsistencies, then my TAs have volunteered to run each and everything manually and make sure that you get the points that you get. A question on Zoom, I've submitted the 3.py files after the update of the autograder. So the current grade would be up to date. Yes, the current autograder results are up to date. Other questions? Yes.
So the assignment asks us to include the results of the coding portion on the report.
Yes.
However, when we go to the grade scope, there's no like pages for us to mark. There's only basically written section.
Oh yeah, you upload the written section and then you just mark out which thing corresponds to what question. Is that the?
Yeah, but what I'm saying is there's no pages for us to mark for the section that's results of our coding portion.
Oh.
There's no way to map pages for the sections of the report where we're supposed to report.
I see. We'll figure it out. I mean, these are the kinds of things that we'll have to kind of work together on. Yes.
They also posted about that. They said that they just will grade everything based on the code.
So then, and everything will just be on question one will just be on the,
Yeah, that.
so is that gonna be okay?
I would like to see some sanity check results, some description on your, of the code parts also in your report. Like any choices that you made, like, design choices, how did you represent your tree and such things? So don't, if your code section is only the code and there is nothing in the report, that will make us a little bit suspicious about it. And we want to know that you did the work yourself. So we want to understand what you did. Yes.
For undergrad students, I think that the collision entry doesn't matter.
No.
So when I submitted, my code for the automated, it still gave me the 4 points for collision entry. Should I write down?
You know what? It could give you 4, it could give you 0. Don't worry about it because as far as we are concerned, it doesn't apply to you. Okay. The other announcement is about homework 2. The original promise was homework 2 will be released today. But I realized that I have not yet covered Perceptron, which will happen on Thursday. So your homework 2 will show up on Thursday. The schedule will get updated. Other concerns? That just means that you'll have a whole Wednesday without any homework. I'll make up for it later. I know. Other questions or comments or suggestions? If you have any suggestions in particular about Gradescope, about making things more efficient, feel free to shoot us a message on Piazza. You don't have to send a message to everyone, just send it to the instructors. Because this is a thing that we are still streamlining. Grading a large class, the previous version, so far we used to manually run everyone's code. And that was, shall we say, unpleasant. So we're trying to optimize things. And any suggestions? Yeah.
Or there's one part that has to make a decision tree.
Yes.
It's a good picture for that.
Yeah.
Like, I'm not-
Yes. Yeah, take a picture. My TAs wanted me to allow pictures. I was the one who was holding them back because, I'm afraid if I allow, okay, let's make it clear. If you take a picture, you're responsible for making sure that the picture looks reasonable, and you're responsible for making sure that it looks like a tree. So, it has to be legible and all that.
So I do it all on paper and then I upload it and then I put it on Google Docs or something, like really big text.
Yeah.
Would it be a bad idea to then give them my page as well and just say additional work?
No, I mean, you can do it if you want, but it's just going to increase the load. Feel free to do it or not. Okay, we're going to go into the content of today's lecture. Today we're going to start a new topic. We're going to look at something called online learning. Just to give you a context of where we are and how we got here. Well, the last lecture was not actually linear models. The last lecture was, we completed the part about linear models, and then we started looking at this question of how do we measure the goodness of a learning outcome? And this is where I was telling you about this little puzzle where I have a monotone conjunction that's hidden, and the learner has to figure out what that hidden function is. And we looked at that one example. And we looked at different ways in which the learner and the teacher can interact with each other. And one of them was supervised learning, one of them was teaching, one of them was active learning. And the thing that we found was, depending on how the learner and the teacher interact with each other, the difficulty of learning measured by how much information needs to get conveyed from the teacher to the learner can be very different. If you have a monotone conjunction with 100 features, with active learning, the learner might need to ask 100 questions. With teaching, the teacher needs to provide only 6 examples in the example that we saw. And with supervised learning, things are not very clear. It's possible that the learner may never get the true function because of biases in the data. So then we have not yet resolved the question of how good a learning algorithm is, Because if we never get the right answer because the data is biased, how could we possibly measure the goodness of a learning algorithm? It turns out that there are different ways to answer that question. And we'll be looking at one of those ways in today's lecture. This is called online learning. Online learning is a certain protocol that the learner and the teacher interact with each other. And if by kind of specifying this learning protocol, we can then start analyzing it and ask, what's the worst case? Are there certain concepts that are in some sense unlearnable unless you have an exponential number of interactions or something like that? This is going to be a sort of a theoretical concept. But then we saw linear models, right? It turns out when the concept of online learning is instantiated for linear models, you get an algorithm called the perceptron algorithm. This is not how things happened historically. Historically, the perceptron algorithm was invented in the 1950s and online learning was analyzed in the 1980s. But this is a nice way of seeing this intersection of measuring the quality of a learning algorithm using a certain protocol, namely online learning, and learning a useful class of functions, namely linear models. This is not the only way in which we'll answer this question at the bottom. There are other ways in which we can answer the same question, and they lead to different kinds of learning algorithms. There's a thing that we call PAC, which we'll encounter after we finish perceptron and such things. And framing this question in the PAC framework directly leads to a learning algorithm called support vector machines, which is not just for linear classifiers, but also for other things. There are other ways also. We can ask the same question from a Bayesian point of view. And being Bayesian about it gives us other learning algorithms for linear models, namely logistic regression. Different ways of answering this question gives us different ways of analyzing the concept of learning and also leads to practical learning algorithms. This is just a preview of a lot of forthcoming lectures. Today, we will look at online learning. In particular, I'm not going to give you introduce online learning in the broadest sense. We'll be looking at a certain subset of online learning called mistake-bound learning. The plan for today's lecture is to look at something called the mistake-bound model for learning. And I'll introduce a sort of a proof of concept algorithm called halving that in some sense realizes that thing without actually being practically useful. But even that proof of concept algorithm turns out leads to certain theoretical results that we can prove without actually having any practical algorithms. And then I'll end up this unit with a discussion about the difference, how representing a certain concept in a certain way can make or break learnability, the difficulty of learning. This is like a plan for this whole unit. Today, now we're going to start off with the mistake-bound model. Imagine that we have a learning problem in a very high-dimensional space. What that means is your instances are represented by very high-dimensional feature vectors. Imagine that your feature vectors are 1,000,000 dimensional. So you have 1,000,000 features that you extract from each single instance. And your learner takes this 1,000,000 dimensional input and has to make a prediction. Now, also imagine that the true function that we are trying to learn is incredibly sparse in this high dimensional space. So you may have 1,000,000 features, but maybe only these 5 features are relevant. And we do not know which 5 are relevant upfront. Or we do not know which ones are relevant. We just know that a small number of features are relevant. We have no idea which ones, so we're going to throw everything into the learning algorithm and hope it discovers that these 5 things are relevant. Now, if we are in this sort of a situation, an interesting sort of a theoretical and practical question is, can we develop learning algorithms where the difficulty of learning, either exactly or approximately or anything, does not depend on this number million, but only depends on the number of relevant features? Or to be more precise, can we develop learning algorithms that depends at most only weakly on the underlying dimensionality? Weakly could mean it depends on the log of the number of features. Log of a million is a small number, so we can live with that, but a million is a large number. And if we can do that, and the second question is something that we'll come to much later, if we can do that, what's the best way to represent the class of functions that we are learning? Can the choice of our representations change the difficulty of learning? I'll give you an example of this. But more specifically, to answer this question, we're going to operate in something called the mistake-driven model. Here's an example of mistake-driven learning. Imagine that you have a learner. That learner does not have a lot of memory. It can remember one example, the current example. Have the current example, it's looking at it right now. And this example, and let's say this new example, the current example goes into the learner. This is X, goes in. And internally, the learner maintains a hypothesis that it may choose to update with time. So currently, the hypothesis is H sub t. When this new example comes in, the learner makes a prediction using the current hypothesis, which is simply ht of x. So essentially what's happening is the learner is a box that is continuously accepting new examples. A new example comes in, the learner makes a prediction and sends it out. Now, that's not learning at all. It's just making predictions. The learning part comes after it makes the prediction. After it makes the prediction, nature then reveals the true label for that example. Nature tells the learner, your prediction was ht of x, but actually the true label is y, some y. And if we think of it from a binary classification point of view, or even otherwise, it's one of two things can happen. Either the prediction was right or not. If the prediction is incorrect, then in the mistake-driven learning algorithm, the learner updates its internal hypothesis using some fixed strategy to ht plus 1. This is the entirety of the interaction between the learner and the concept. In each round, so you can think of this as an infinite loop. At each step, the learner keeps waiting till a new example shows up. When the new example shows up, the learner makes a prediction. After that, nature reveals the true label. And if the true label does not match the prediction, the learner can update itself. It's incredibly simple. This is about as simple of a learning algorithm as you can think of. The learner does not do anything if there is no mistake. And that's why it's called mistake-driven learning. So the reason this is very simple is you only need to define two things to instantiate this kind of a learning algorithm: how prediction works and how the update works. These are the only two steps that matter, and everything else is fixed in this framework. And the question to think about is, can such a simple scheme ever learn interesting things? And what does it mean for it to learn? How do we define that the notion of this learner actually learning the true concept? Before we move on, any questions about this simple framework? Yes.
So with the updates that we're saying, update h sub t to h sub t plus 1, is that saying the hypothesis is being moved to the next time step? Or
No,
is
no.
the hypothesis being updated to the true assumption?
There's no notion of truth here, because the learner does not have the true function. Remember, the hypothesis is a function. The learner has a certain function inside itself, ht, and it has made a mistake in step 4, which means it has an internal update rule that allows it to change that internal function to something else. We are calling that something else ht plus 1.
Okay.
based on, and the entire algorithm is defined by how the prediction works and how this update works. So if I specify these two subroutines, we have this whole framework. Okay. Other questions?
So, I mean, right?
No, the loop is infinite. If the prediction is correct, the learner does nothing. It got it right. There's nothing else to do. It just waits for the next example. Yes. That's a good question. It does not remember anything about the past examples, except to the extent that may be stored inside this ht plus 1. Maybe ht plus 1 contains everything that's seen so far. Because remember, I'm leaving these two highlighted things unspecified. Maybe the update step involves remember everything. That's not a good idea, but it could do that. Other questions? So let's formalize this a little bit more. In particular, I want to use this particular model of a learning algorithm to define a notion of goodness, or to define a notion of successful learning. That's what we're going to do inside this model. And I'm going to call that mistake-bound learning algorithms. So let's work through this one step at a time. We have an instance space. I'm calling that capital script X here, this thing here, X. And there is a hidden target function that we do not have access to. That target function maps your instance space X to a binary label. We'll work with binary classification for now. The label can be 0 or 1. And it just so happens that that nature in deciding to choose F as the true concept had a set of functions. I'm calling that capital C, and it picked the true concept from that capital C. So, for example, the true concept could be all linearly separable functions. And nature has decided that for this particular task, the true concept is the target function is one of those linearly separable functions. Or maybe the true concept is Boolean conjunctions, which we saw in the previous lecture. We don't say which one, but it's a Boolean conjunction, and nature chooses one of them as the real function. One way or another, there is a certain set of functions that we are assuming nature has access to, and it picks one of them. Eventually, the thing that's going to matter is the size of that concept class. How much are we allowing, how much freedom are we giving nature to pick the true function? And we'll also assume that the size, the dimensionality of these instances is n. So we have n dimensional instances. The learning protocol is the one that we just saw. The learner sees an example, x, little x, that was randomly chosen, and it makes a prediction, h of x, and after it makes a prediction, it's given the true label f of x. That's the feedback step. And internally, it does some updates, and maybe h gets updated to something else. Okay? This is the entirety of the learning protocol. Now, under this protocol, what you should think about is how can you measure success? Because this is an infinite loop, right? There's no training set, there's no test set, which is how you're doing things in your homework. It's an infinite loop. How do you measure success? How do you measure success for one example? Any ideas? Yeah. Be a little bit more precise. What do you mean by that?
If prediction is correct.
Meaning h of x equals f of x. Yeah. So the learner gains a point if h of x is equal to f of x on this one example that just showed up. Or you can think of it as, because it's an infinite loop, let's say the learner loses a point every time it makes a mistake. You can measure that. So The learner makes a mistake whenever h of x is not equal to f of x. And we can count how many times is the learner making a mistake on a certain sequence of examples. I can do that, right? I mean, given a sequence of examples, I can count the number of mistakes. So does that make sense? Let's give that concept a name. There's a true concept. There's a true function f and a certain sequence of examples. I'm calling that capital F. And there's a learning algorithm A. I can count how many mistakes has this learning algorithm. By the way, this learning algorithm is entirely decided by how the prediction is made and how the update happens, because that's what we saw. That's the game we are playing. So we can count how many mistakes does this learning algorithm make on a particular sequence of examples for if the target function were f. So for instance, imagine that you have these sequence of examples. I have 9 examples here. And there are mistakes on example number 0, 2, 4, and 6. And maybe after that, forever, going ahead, all the way to infinity, there are no more mistakes. Could happen. If that happens, then the number of mistakes that this particular instance of learning saw was 4. At this point, there's no basis for knowing whether this is a small number or a big number. It's just 4. The reason we can't tell whether this is good or bad is because there's something here which the learner really does not control. It does not control which example is going to show up next. Maybe it got really lucky with this sequence. Maybe it got really lucky and it made its mistakes early on and quickly figured out what the true concept is, right? That could happen. So really, we need to be looking at every possible sequence. And we can ask, for each sequence, how many mistakes are being made? For every possible sequence in which the instance space can be presented to the learner, we could imagine this sort of an infinite parallel universe, where in each universe a different sequence is presented, and we can count how many mistakes are made. Right? Questions before we, yes.
How many sequences ought we consider when trying to figure out the number of mistakes?
Every single one of them.
Every single one.
Yes, and we'll see why in a minute.
What if that's in infinite set?
It is most likely going to be an infinite set, which is why this is a tool for analysis. It's not a experimental thing. There's a question on Zoom. Is there not a risk of overfitting on the training data with mistake-bound algorithms, since we are literally trying to find the optimal edge that fits the training data? If we are not careful, every single learning protocol can overfit. But it turns out that there is not necessarily a risk of overfitting in this case any more than other instances. And I don't want to get into the technical details yet, because we'll be looking at that as we go along. In this case, let's assume that there is a true concept and we want to learn it in a certain way. And I'll talk about what that certain way is right now. So I have this concept, this expression here, M A of f comma s is simply the number of mistakes that the learner A makes on the sequence S if the true target function was f for a particular sequence S. And I said we need to consider every single sequence in order to say something. The way we say that is, if consider, I think there's a mistake here. Yes, there's a mistake here. This should be a C. Can you remind me afterwards? Yes, there's a mistake here. Now, before we talk about all possible, there are many mistakes here. So I'll write this more correctly. This expression is entirely wrong. It should be max. Consider, so if we have a sequence S and the true function f, and I can measure the number of mistakes the algorithm A makes on it. Now consider every possible sequence, and let's consider the absolute worst sequence. So I could ask, among all the sequences, that exist, what's the maximum number of mistakes that the algorithm can make if the true function were f? Right? It may seem like this could be infinite, but we'll see why that matters in a bit. But we do not know that the target function is f. We have no idea that the target function is f. The target function could be anything inside the concept class C. So let's assume that some functions in this concept class are easy to learn and some functions are hard to learn. So we are trying to now consider the worst case situation. Among every single function in the concept class, find the most difficult function, f. And for that most difficult function, consider the most difficult sequence of examples that can be presented to the learner. It's an adversarial situation. The adversary picks the most difficult concept and the worst way in which to present the concept, and then forces the learner to interact with that concept in the protocol that we just saw. And under that bad sequence and for the bad function, we can ask, how many mistakes will this learner make if this were presented to the learner? Again, we can't run this experiment because the sequences are infinite. The function could also be exponentially large, the number of functions, or possibly infinite. We can't run this experiment, but it's a conceptual device. Okay, it's the maximum. So I'm going to call this quantity here MA of C. MA of C is for this concept class C. If nature gets to pick its function from the set C, we just do not know which one. For the algorithm A that we are trying to analyze, is what's the worst case number of mistakes that the algorithm can make on any function inside this concept class and any sequence in which examples are presented to the learner. Before we go ahead, I'd like to pause for questions. Yes.
A is the hypothesis.
A is the learning algorithm, the way in which these two things are defined. I'll go there in a minute. The prediction rule and the update rule. There is a certain learning algorithm which is entirely defined by these two things, that maybe someone comes to you and says, I have the world's best learning algorithm. Defined by, in this protocol, I have the world's best learning algorithm, which means that I have given a certain definition of the prediction step and a certain definition of the update step, and you are skeptical. And you want to break that algorithm. And you're saying, I'm going to give it the worst possible function to learn and carefully construct the worst sequence of examples and count how many mistakes it makes. Yes.
So for MA of C, we don't know what the function in C exactly is,
Yes,
right?
we don't.
Okay.
This is a conceptual device that we'll have to play with. I thought I saw another hand. Yes.
Well, you said this function chooses the most difficult function. What does that mean?
The one that forces the maximum number of mistakes.
So kind of like the worst function.
Yes. Other questions? Yeah. What do you mean? How does it get these functions? Get from where? Oh, you don't. We don't need to yet, because we'll see that once again we're going to define something, and then without actually worrying about which function it is, we can prove some theorems. Turns out, which is kind of a cool thing. I never thought about that, but yes, without worrying about which function is the worst one, we can make certain statements. In particular, the thing that I'm going to define now is I'm going to tag this algorithm with a certain property. I'm going to say that it's called a mistake bound algorithm if this quantity M A of C, the worst function, the number of mistakes made by this algorithm on the worst function in C for the most adversarial sequence of examples, if that quantity is polynomial in the underlying dimensionality n, I'll say that this algorithm is a mistake bound algorithm. Another way of saying that is, It doesn't matter if nature picks the most difficult concept to learn inside the set C. It doesn't matter if nature chooses the most difficult sequence of examples in which that function is being presented to the learner. If the algorithm makes only a polynomial number of mistakes in the dimensionality, then this algorithm is successful. I'm giving it a tag. I'm calling it a mistake-bound algorithm. The important thing to note here is I'm just defining this concept of mistake-bound algorithms. I haven't said anything about whether there exists a mistake-bound algorithm. Maybe this is a vacuous definition and nothing fits this criterion. Turns out I'll show you very soon that there is something that fits this criterion. But the reason I'm saying that is all I'm doing here is defining something. I have not shown you any examples of this. I have not shown you any proof of existence of such algorithms. We'll see that in a bit, but it's just a definition. Any questions about the definition? It's n power something, roughly. It makes the number of mistakes that is made is less than, sorry, not n power something. It is, yeah, it is n power some constant. So for some constant, it's less than that. In particular, it is not something like 2 power n. It's not exponential. Because an exponential expression is going to be bigger than any polynomial. And we're talking in the order of magnitude here. And we don't even want to worry about what is the degree of that polynomial. Even a 100-degree 100 polynomial fits this thing, even though it's a massive expression. Yes.
So are we saying that it's a mistake-bound algorithm if it's not NPR?
Well, we don't have anything about NP hardness here. NP hardness is about computational complexity. This is specifically about number of mistakes. There's nothing about computational complexity. Maybe inside this update step that I've not shown, that maybe something maybe it's solving an NP hard problem internally there or not. We have not talked about computational complexity at all. That's an interesting point I want to, I'll probably mention much later in the semester. If you've taken algorithms before, you might have noticed, you might have seen a discussion about computational complexity. How much computation needs to be expended in order to solve a certain problem? That's the loose way of thinking about it. In machine learning, we have a different kind of complexity called sample complexity. How many examples, how much interaction needs to happen between the learner and the concept to learn the concept perfectly or well enough or stop making mistakes or something. So here we are talking about a version of something called sample complexity. We'll talk about sample complexity more rigorously when we get to pack learning, but it's different from computational complexity. So just to quickly revisit this thing that I just said, the algorithm A is called a mistake-bound algorithm if the number of mistakes it makes, the maximum number of mistakes it makes for any sequence of input for any function in C is still a polynomial. That's what I just said. This is a property of the algorithm with respect to this concept class C. Maybe the algorithm A is really good for this concept class. Maybe it's not good for some other concept class, right? Every concept class might have its own special algorithm that works only for that. We can also ask about a set of functions, a concept class, about the difficulty of learnability of a certain set of functions. A concept class is learnable under this mistake-bound model if there exists a mistake-bound algorithm for that concept class. In other words, the concept class is said to be learnable if there exists some algorithm. I don't even need to show you that algorithm. I can just prove through some circular means the existence of that algorithm. If I can do that, provided the algorithm makes only a polynomial number of mistakes for any sequence of examples for any true function inside that concept class. If that happens, then that concept class is learnable. Once again, all I have done here is just tag a set of functions, the concept class, as being learnable or not. I'm using a word learnable because it's kind of, it makes sense to us. But I want you to reflect upon whether this is really learning. whether this matches your intuition of what learning means. What we are saying here is that this this set of functions, there is some nature gets to choose a function from C and it hides it. And then you come in and say you're able to prove a theorem that says, I don't know what that true function is, but there must exist some learning algorithm that operates in that in the mistake bound mode, in the mistake bound framework, that does not make more than polynomial mistakes, no matter which function nature chose, and no matter how nature presented its examples to the learner. You don't even have to present the algorithm. You're just saying that set of functions is learnable or not. Any questions, comments?
Has to be from polynomial and not other real.
Linear is the smallest polynomial, so linear is a special case of that. Essentially, exponent in computational complexity in theory or in CS theory, exponential is bad because exponential grows too fast, and polynomial does not grow too fast, and we consider it as a victory if we can prove that something is only polynomial. If you can make it, linear, that's great. If you can make it sublinear, that's even greater. But polynomial is about the worst good thing that you have. This is a very pessimistic definition. The interesting examples that we'll encounter will not see big polynomials. We'll see polynomials of degree 2 or even 1 or less than that even. Did you have a question?
Yeah, I'm just trying to put these two pieces together. So the concept class is learnable if this algorithm A exists and satisfies MAC being a polynomial.
If this property is satisfied.
So it's learnable if that A exists and satisfies it.
Yes.
Got it.
Once again, I want to make it very clear. I have just, given you two definitions. I might be wasting your time and giving you definitions of things that don't exist in real life. Right? This is just a definition. I'm defining an algorithm to have a certain property, and maybe no such algorithm exists. I'm defining a concept class to be learnable if some algorithm exists that has this property, and maybe no such concept class exists. Right? And maybe, well, it turns out that it does, but all I have done is show you definitions. When you see a definition of something like this, you should always ask yourself, why is this definition interesting? And are there interesting lessons that we can learn because we decided to name this property with something, and bring it up in class, for example. I'll talk about why this definition is interesting through the rest of today's lecture, because I'll show you a proof of concept mistake bound algorithm. And without proof, I'll actually point out that that proof of concept mistake bound algorithm is almost like a test for whether Boolean functions can be learned or not, certain classes of Boolean functions. The other thing I wanted to mention is this is not the most general setting for online learning. Online learning has a similar sort of a protocol. In online learning, the learner encounters a new example and it makes a prediction. And then something else happens. Nature does something and it does something to the learner, and the learner gets to choose to make an update if it wants. In the mistake-driven or mistake-bound setting, the something else that happens that nature does is it reveals the true label. And then the learner sees the true label and its prediction, and if there's a mistake, it updates it. But the more general version of online learning is where the learner makes a prediction, or let's say the new example comes in. The learner makes a prediction, and based on the prediction, nature decides to give it a reward. The reward could be the degree of correctness of this prediction or something like that. And that's one version of it. Or there are variants of this idea, and there are also variants of analytical tools for understanding online learning. The mistake bound model is in some sense, the simplest one. The more general version of it is something called regret, which says the learner makes a series of predictions as it goes along. And then after this episode of examples is done, the learner then looks back and says, if only I had seen this whole sequence at the very beginning, I could have done much better. I could have made better predictions. So how much regret does it suffer at the end? In a certain sense, in a mathematical sense. We will not look at it, but if you're interested in this sort of analysis, you should follow up on it. You should, and the thing to search for is regret bounds. Just like we have mistake bounds, there are algorithms that are called regret bound algorithms. We will not be talking about that in the class. Online learning does not make any assumption about the way in which examples are presented, the sequence of examples, because it assumes that nature is adversarial. It assumes that nature is going to present the examples in the worst possible way. Because the definition says, among all the sequences in which examples could be presented, consider the most difficult one, the worst one. It does not really matter because, well, it may matter, but really the only thing that matters here is the number of mistakes. So let me give you an example for why this is both good and bad. On the good side, if you are deploying a learner in the real world, the only thing that matters is if it encounters examples and makes mistakes or not. And that's pretty much all that matters. However, it's entirely possible that your learner is stuck in some loop where it keeps seeing the same example again and again. It may see the same example again and again. It sees an example and it remembers the label after the true label is revealed. And then after that, it never makes a mistake. Would that count as win? In this model, it does. In this model, it counts as a victory because it never makes mistakes anymore. Who cares about the learner learning the true function if the examples that are presented are so strongly biased that the learner never encounters anything else again? That's a good thing and a bad thing. It's a bad thing because it's not really about learning the true concept. It's a good thing because it measures the behavior of the learner in the environment in which the learner is supposed to operate. So there are strengths and weaknesses of this learning protocol. It's a simple and intuitive model, and it can be widely applied. It's one useful way to use case here might be, imagine that you have a data set that is so large that you can actually never let the learner explore that entire data set. So the only way to have the learner interact with the data set is maybe you see one or a small set of them and make an update and then never revisit those examples again because you don't have too much memory. So in the streaming setting, I want you to think about what this has to do with the real goal of machine learning. The real goal of machine learning from lecture 1 was generalization. If a learner stops making mistakes on the sequence of examples that it encounters, has it generalized to unseen examples? Yes and no. And it turns out that you can justify that and also argue against it. And I'll leave that as an exercise for you. The good news for this protocol of learning is that it makes no assumptions about the distribution of data. It does not care how examples occur in real life. As long as the learner encounters one at a time, it's possible that the data could be in a worst case sort of a setting. It does not require too much memory, provided that update step does not do strange things like remembering every example. On the other hand, it might be too simple because maybe if you're only counting the number of mistakes. So remember, the mistake bound model says, I consider a certain learner to be successful if it makes a polynomial number of mistakes. And after it makes a polynomial number of mistakes, it will never, ever in the future of this program make mistakes. That's a fantastic guarantee, but what it does not say is when those mistakes will happen. Maybe, let's say that I have proved to you mathematically that this particular learner will make only 2 mistakes in its life and never again. And maybe it made 1 mistake on some examples, and you're like, yeah, there's only 1 mistake left for it to make. Let me deploy this learner in the wild, and it's a self-driving car, let's say, and it makes a mistake at a very, very bad time. So it does not tell you that this protocol does not talk about when the mistakes will happen. It only says there will be a limit to the number of mistakes. And despite its simplicity, many of the interesting issues that we face with machine learning already crop up here. In particular, even in this simple model, we can prove that certain concepts are unlearnable. And we can prove that certain concepts are learnable efficiently. By efficiently, I mean data efficiently. And it turns out that these analyses actually can be systematically converted to other kinds of learning protocols without too much effort, which is why this is an interesting object to study. Are there any questions? Let's now get some examples. Like I said, I only told you about this idea of a mistake-bound algorithm without actually presenting any real algorithms. So let's look at an algorithm called halving, which it turns out is a mistake-bound algorithm, which it turns out can be a mistake-bound algorithm on certain concepts. So this is a proof of concept algorithm. This is not something you can implement in real life. It's because there's going to be a exponential hidden inside it, but there are certain interesting properties that it already has. Before presenting halving, I'm going to present a really bad algorithm first. A bad algorithm that already also has interesting properties that we will contrast against halving. So let's work with a finite set of functions. Nature chooses the concept class C, which is finite. And our goal is to learn some function that nature has designated as the true function. That function is f here. First, let me introduce an algorithm called con. Con is short for consistent. It's a very simple algorithm. It proceeds in rounds, like all mistake-driven learning algorithms. So when a new example comes in, the ith example comes in, con maintains a set Ci, which is a subset of C, that is consistent with all the examples that have been seen so far. Okay? And then it has to, remember, a mistake-bound algorithm has to make a prediction and then update itself. The way it predicts on this new example is it picks a random function from the set of functions that it has that are currently allowed and uses that function to make a prediction. And maybe that function made a mistake. If it made a mistake, then it removes all the functions from C that disagreed with the tooling. So for instance, I'll give you an example. Let's say the set C consists of 4 functions. Let's say these are all Boolean. And in the beginning, it starts off with the set, it keeps in memory all these functions. And some new example comes in X. And what this, I could ask without actually doing anything, I could ask, what was the label that F0 made on this? What's the label that F1 would give to X and so on? Let's say F0 says the label is 1, F1 says the label 0, and 0. What con does, it it randomly picks one of these functions. Let's say it picks f2, and it says the prediction is a 1. So that's the prediction step. And then nature reveals the true label. Sometimes in the machine learning literature, the true label is also called the gold label, short for gold standard. And let's say the gold label is 0. That means the prediction was incorrect, which means the mistake-driven update kicks in. And the update step is to say, you want all concepts that are consistent with all the examples seen so far. Notice that F1, F0, and F2 are inconsistent because the true label is 0. So then this, let's say C0, the initial set is C0, then it goes to C1, which is the set F1 and F2. No, F1 and F3. And now we are ready for the next example. This is the learning protocol. Does this make sense? It's very simple. It also has a really bad property. It has to remember the whole set of functions that that are active, but you can imagine this algorithm without actually implementing it. The important point to note is when there is no mistake, if the gold actually had been 1, then C0 does not get updated because we are in the mistake-driven protocol. When there are no mistakes, C0 still remains. Right? So it's not very hard to see that if an update ever happens, you are actually going to remove some functions. Because at least one of these functions made a mistake. The example, the randomly chosen function that was used to make the prediction made a mistake. So if any update happens and Ci gets converted into Ci plus 1, Ci plus 1 will be a smaller set of functions, just like the example we saw. Right? Now, if a mistake is made on the ith example, then Ci plus 1 is a subset of Ci. If there is no mistake that's made, then Ci plus 1 will be equal to Ci. Which means whenever there's a mistake, Ci plus 1, the number of functions in Ci plus 1 is strictly less than the number of functions in Ci. I would argue progress has been made because we are quickly narrowing down, not quickly, we are narrowing down to, we've removed some confusing functions from the concept class, and eventually we'll stop making mistakes because we'll come to the true function that's inside this set. How many mistakes can Con make? What's the worst case number of mistakes? There's one suggestion, which is the number of functions in C, which is just the size of C. Can you, or maybe someone else, justify this or update it? Actually, can you justify it? Why is it the number of functions?
We run out of functions.
Sorry?
We run out of functions.
We run out of functions. Eventually, if at every mistake, we are going to keep removing functions. There are only these many functions, and importantly, this is a finite concept class. We will run out of functions. You're almost right. There is one fix that I would make to this. Yes.
From total functions -1, at least one would be right.
-1. Why do you say that?
I mean, whatever we have said, from that, at least one can be fulfilled that requirement, right? What we are looking for.
Let me edit what you said. At least one will satisfy that requirement because f, the true function, is in C. That true function will never make a mistake because that's what nature uses to label things. No matter what happens, that function will never get eliminated. So the number of mistakes that can be made is at most the size of C -1. Any questions about this? The Con algorithm does not make more than size of C -1 mistakes. Yes. The question is, how does noise factor into this? For the purposes of this lecture and today alone, we're going to pretend that we live in a universe with no noise. Because it turns out, even without noise, we can show that some functions are unlearnable using this tool that we'll develop. Other questions? Yes.
So why is this a bad mistake bound algorithm?
Let's come back to that question. There are two reasons for why this is a bad mistake-bound algorithm. I'll answer one of those, and then the other one, which is more interesting, I'll tell you later. Okay. The first reason why this is a bad mistake-bound algorithm is because it has to remember every single concept in the function class. How many Boolean functions exist? 2 power n. If you have 4 features, it is 2 power 4. It's 2 power 16. Now, that doesn't seem like a large number. We have computers. My phone can hold more than those many things. Okay, let's say we have 1,000,000 features. This function, this algorithm is not something that should ever be implemented. Please don't implement this because you'll run out of memory. It's just a conceptual device. Now, in fact, I have not yet told you whether this is a mistake-bound algorithm or not. All I have said is Con makes at most size of C minus 1 mistakes. The definition of a mistake-bound algorithm is the number of mistakes should be polynomial in the number of features. So to decide whether Con is a mistake-bound or not, we need to know what the number of features are. Sorry, what the size of C is in terms of number of features. If you have 10 features and my concept class C is all possible Boolean functions, the number of mistakes is 2 power 10. And the Con algorithm will make 2 power 10 minus 1 mistake. Let me write that down. 2 power. Definitely not, in fact, let me, instead of 10, let's say it is n for number of features. That quantity is definitely not polynomial in the number of features, right? So Con is not a mistake-bound algorithm for that concept class. Turns out there are concept class. We will come to the. I want to contrast this against halving, which we'll talk about next. But importantly, I have shown you this sort of. This is a proof. It's a theorem that says Con makes at most size of C minus 1 mistakes, and this slide is informally showing you a proof. This theorem is not going to answer whether Con is a mistake-bound algorithm or not, unless you tell me what the function class is, and then I need to count the number of functions inside C. Let's now consider a different algorithm, halving. The halving algorithm, I want to contrast this against Con. Once again, we have a finite concept class, C, just like with Con, and our goal is to learn some function inside the C. The way halving works is it initializes C0 to be the entire set of functions, just like Con did. The initial set of functions that are under consideration is every function that exists in our set, which is all of C. At each step of learning, whenever an update is made, halving will somehow trim the set of functions, just like Con did. And learning ends when there's only one function left, because when there's only one function left, we know it's the right answer because we knew that there was one function inside the set that was correct. And if our set of valid functions, if our set of functions is only, if our operations that we do internally here, that I've not shown from here to here, does not accidentally remove the right function, that's the only thing that will be left. The correct answer will be left in the set. So let's see what's going on. When a new example arrives for a mistake-bound algorithm, I need to first make a prediction. What Con did was it picked a random function from the set that is currently in consideration, and it uses that as a representative for the entire set and says the label is that. What halving does is it asks every single function for the label. every single element of the set Ci, remember the set Ci is a set of functions. It asks every single one of them for the label, and if more of them say 1 than 0, then it will predict 1. If more of them say 0 than 1, it will predict 0. So it will pick the label that a majority of the functions have. Does that make sense? Mechanically, it's just asking every function that for the label and asking and picking the most common prediction. I've just written that here in math. The size of the set of functions that predict 1, if it is greater than the number of functions that predict 0, then the label is 1, otherwise the label is 0. Now, it's time for a possible update. If it predicts a 1 and nature says, oh, you know what, the label is 0. Or if it predicts a 0 and the nature reveals that the true label is a 1, then an update is triggered. If the prediction is not equal to the true label, f of x, then you update the set Ci to construct a set Ci plus 1 by eliminating all the functions that were incorrect. Just like with con, you eliminate all the functions that were incorrect, and you'll be left with a smaller set. Yes?
This means we're only using the M function.
We are using what? No, there's no assumption here. The only assumption here, the question was this, are we assuming that we are using only the AND function? No, we are assuming that our nothing more than the fact that our concept class is finite. That's pretty much all we have. So if I could have 4 functions, again, f0, f1, f2, and f3. Example x comes in, and let's say all of these things predict a 0 and f3 predicts a 1. The true label, well, we don't care about the true label. The predicted label is a 0. We don't know what the true underlying functions are. It's just a finite set. Maybe the predictions are 0. Well, not maybe. Here, the majority labels are 0. So the prediction is a 0. And let's say then the true label, f of x is 1. This is h of x. This is the consensus prediction from this step here. And if the true label is 1, that means a mistake happens. So if this was Ci, then Ci plus 1 is, well, you remove all the functions that make a mistake. In this case, there's only 1. So you have f0, f1, and f2. Every one of those is, yes, every one of those is a function. We define the concept class in a certain way. The interesting question to think about is how many mistakes can halving make? We did this analysis for con, right? In con, no matter what happens, at least one function will get eliminated whenever there's an update. And so the number of mistakes will keep is bounded by the number of functions minus 1. How many mistakes can halving make? Any ideas? Oh, sorry, I heard someone say something that it's the same, right? There's one word for the same, yes? The same?
I'm thinking it's, just looking at this example here, it would be the number of error functions, or like the number of mistakes divided by the total number of functions, or like some, I don't know how to best describe it, but
you are arguing that it's different.
yes.
And it's a number, by the way. You can't have a fraction, but it's you can. Never mind. Okay. Let's analyze this. It turns out it's not very hard to analyze. And the way to think about this is the following analogy, which I personally find very useful. Con is like linear search in a list. Halving is like binary search. Let's see why. Suppose the algorithm makes n mistakes, which means it starts off with some C0, and then it proceeds through a sequence of examples. Eventually, it makes a mistake, and you get a C1. Eventually, it makes another mistake, and C2, and eventually Cn minus 1, and then finally Cn. And let's say the set Cn has only one example, one function in it, which means learning has stopped. So the size of Cn is 1. Let's consider the step that took us from Cn minus 1 to Cn. An example came in, and more than half the functions made a certain prediction which was wrong. And then every function that was wrong gets eliminated, which means more than half the functions get eliminated. So the size of Cn has to be less than, it's the minority set inside Cn minus 1, because the majority set was the label, produced the label which was incorrect, and they got eliminated, and we are left with a smaller subset. So the size of Cn must be strictly less than half of the size of Cn minus 1. I see one head nodding. I see confused faces. So ask me questions. Yeah.
So if you, I guess, per se got lucky,
Yes.
you would always keep that like one function that gives you the wrong answer. Because the majority of the functions give you the right answer.
Yeah, entirely. Absolutely, yes. Absolutely, yes. But that's you've kind of gone a little further ahead than I would like, but you're on the right track. To illustrate this thing, I have a set of functions. Every point here is some function. It's a finite set. There are only a finite number of points inside this. When the new example came in, you asked for a label from every one of them, and then it turns out it was a mistake. The majority label was a mistake. Let's say all of these functions, these dots here, predicted a 0, and this one here predicted a 1. The only one function, this function here, predicted a 1, and everything else predicted a 0. Because we are taking the most common label inside the set, the number of 0 predictions will be at least half. So more than half of these functions predicted a 0, and it turns out it was a mistake. So this entire set gets eliminated. And then we are left with only this one function because it was correct. By construction, the process of going from the set Cn minus 1 to the set Cn would have removed at least half the set of functions. Just by definition of how the prediction happened. The prediction is 1 if more than half the functions make predict the label 1, and they all get eliminated. Yes.
What if we just reverse the case, like all of them predict correct and only one function predicts wrong?
If all of them predict, yeah, that's a good question. That's related to what you asked, so I'll explain that. Let's consider only 3 functions, okay? So I have this function here, I'm calling that f0, f1, and f2. And let's say f0 predicts a 0, f1 predicts a 1, and f2 predicts a 1. And what is the consensus? What's the most common label here? It's a 1. So this whole thing turns out a 1. And now nature reveals the true label. Let's say nature reveals the label 1. There is no mistake. If there's no mistake in this protocol, we don't make an update. So these 3 functions all remain. And that's the example of this extremely lucky function f0 that survived even though it was wrong, because the learning protocol allows it to continue. Yeah.
So suppose there are multiple examples where the predicted label and the true label is the same, and we never eliminate the F0.
Yes.
So how will the algorithm end?
It never ends. It keeps going on forever till the sets come down, till the set becomes a singleton.
Remove the 0.
It does not remove the 0 simply because we are still operating inside this very, very, very simple protocol where updates happen only when there's a mistake. And you could have removed the 0. That's a different learning protocol, and it has its own analysis. In fact, turns out it doesn't change the underlying point too much. I mean, from a order of magnitude point of view. Yes.
That's all because it's not considered a mistake.
Yeah, exactly. It's not considered a mistake.
If we don't remove 0, then the protocol never stops.
The protocol never stops. This protocol continues to infinity.
Very bad.
Well, it turns out this is interesting. It's very simple. Let's not have value judgments here. It's very simple, and despite that, we can prove that even in the simple learning protocol, some things are provably unlearnable and some things are provably learnable, and nothing's going to change otherwise if you change the protocol. Okay, let's make this. Let's go on a little further. So when we went from Cn-1 to Cn, we did so by cutting out more than half the set of functions. Similarly, when we went from Cn-2 to Cn-1, we eliminated at least half of Cn-2 because of the same argument. I can keep doing that all the way down to the initial set C0. So here I'm multiplying by half. Here it's half times another half. Every time there's a mistake, I'm accumulating another 2 in the denominator. So I'm left with half 1 over 2 power the number of mistakes. N is the number of mistakes. Times C0, the size of C0. C0 is the entire set of functions, the concept class itself. So C0 is simply the size of C0 is the size of C. So the final number of mistakes, the size of the final set, Cn, which is equal to 1, which is when learning stops, is going to be less than 1 over 2 power n times the size of C. We care about that quantity n because I want to know how many mistakes are being made. So let's just reorganize this thing. And we know from just simple algebra that this means the size of C should be more than 2 power n, or taking log on both sides. That means the number of mistakes, n, is going to be less than log to the base 2 of size of C. The number of mistakes is going to be less than a log of the number of functions that we have. This is the analogy to binary search, by the way, as just a reminder. We saw 2 algorithms. Halving makes a logarithmic number of mistakes in the size of the concept class. Con makes a linear number of mistakes in the size of the concept class, size of C minus 1. We haven't said anything about whether this is a mistake-bound algorithm or not, but now we have a blueprint for starting to analyze concept classes. I can ask, given a concept class, C, is it learnable in the mistake-bound model by halving? Is it learnable in the mistake-bound model by con? Because we know the worst-case number of mistakes it makes. And then I can ask, if it is learnable in the halving model, does this mean anything interesting? The halving algorithm is hard to compute, but despite that, it turns out that halving is optimal. That means for the classes of all Boolean functions, no algorithm can make fewer mistakes than halving. We are not going to prove that. It doesn't matter what the true function is in this set of Boolean functions. No algorithm can make a fewer number of mistakes than halving. That means halving tells you something very interesting about the concept class, even though it's actually a terrible algorithm from an implementation point of view. And that's the answer to your question about it's such a bad algorithm. And yet, because of the fact that it's optimal, it tells us something theoretical. I'll stop here. We'll pick up on Thursday and then wrap up this section. Don't forget the homework. And if there are questions, please post on Piazza.